This is now the 5th episode on explosions. So we know by now what this plot is. It shows the growth of the blast radius of an explosion over time. It is representative of many explosions, large and small, but it is not any explosion. It is the first atomic test, Trinity, in July 1945. Following Taylor, we know that in this time range, the blast radius is proportional to time to the power 2/5. We know that this power law can be understood as a scaling law, relating the kinematics of the radius to the mechanical ratio between the energy E of the explosion and the density ρ of the ambient air. If we want to look more serious, we know that we can actually turn the approximation into a strict equality by introducing a dimensionless constant, delta, always not far from 1. In the last episode, we wondered about what happens beyond the time range of Taylor's regime. We discussed the late dynamics of explosion and highlighted the importance of the length scale D, set by the ratio of energy and pressure. This length provided an end to the explosion. It's now time to face the beginning of the explosion, where it is quite clear that Taylor scaling fails. In this 5th episode on explosion, we will discuss the early dynamics, before the time range abiding to Taylor scaling. The first couple of data points deviate from the 2/5 scaling. The earliest data point is at 0.1 millisecond after detonation, and at this time the radius of the explosion is just barely greater than 10 meters. The front has not reached the ground yet. The bomb was detonated 30 meters above ground, at the top of a tower. For the next 3 points, the radius continues to grow. The scale bar is 100 meters. In all of these pictures, the blast has not touched the ground yet. Why is it that the last 2 pictures fit with Taylor's regime, whereas the first 2 deviate from it? What is going on between what seems to be 2 distinct regimes? Why can't the explosion abide to Taylor's regime all the way to its very first instance? Let's imagine for a second that it did. In this imaginary scenario, the explosion would remain on the red line. And there are a few reasons to discredit such an imaginary trajectory for the very early explosion. At some point, the blast predicted by Taylor's regime would become smaller than the bomb itself, which was slightly less than a meter in radius. And if we were to investigate more closely the synchronization of the detonation process, we would realize that any time below around 1 microsecond is associated with such a large margin of error as to be practically meaningless. And even if we imagine the tiniest possible bomb and the fastest possible detonation process, there is another limit that is even more impenetrable. That is the speed of light. Once the red line of Taylor's regime crosses the white dashed line, this would imply that the front of the explosion is moving faster than light, which is beyond our willingness to entertain absurd scenarios. Nothing can be on the left of the white dashed line if the speed of light is to remain an absolute maximum. So, one way or another, there must be a regime coming before the 2/5 scaling by Taylor. In this episode, we're going to see that this initial regime is very often at a constant speed, that is parallel to the light speed curve, but with an initial speed c0 smaller than the light speed. This initial speed depends on the energy of the explosion, as well as on the mass of the bomb. For Trinity, we only have a couple of data points departing from the 2/5 scaling at very early times. Assuming that the initial regime is at a constant speed, this speed could be estimated from the radius of the first data points at 0.1 millisecond, and we would get something like 100 kilometers per second. The pictures imply that initially, the explosion front moves at 100 kilometers per second. But why should the initial regime be at a constant speed? We could assume a more general power law with an unknown exponent that we can call alpha prime so as not to confuse it with Taylor's regime. The constant speed case just corresponds to alpha prime equals 1. Since we don't have much data on the very early explosion, a lot of exponents could a priori be valid. Yet, the exponent cannot be arbitrary. If this regime extends all the way to detonation, we know that its exponent must be greater or equal to 1. Why is that? We've seen already that if the size is a power law of time, then the speed is also a power law, with an exponent alpha prime minus 1. So alpha prime must be 1 or greater if we want to avoid a divergence of the speed when the time goes to 0. This condition still leaves a lot of possibilities. In some cases, the front may initially accelerate, that is alpha prime strictly greater than 1. And maybe we'll talk more about this another time. Today we consider alpha prime equals 1. That is an initial regime at constant speed c0. And we ask, where would this speed come from? We can reasonably assume that this speed depends on the energy of the explosion. So we know the drill. We can try to express the speed as a mechanical ratio. The mechanical quantity Q is not yet known, but matching the dimensions constrains the dimensions of Q. The mass cancels out, of course. We then have to match the space and time dimensions. This leads to a system of equations, which we can use to express beta and also to find a relationship between the space and time exponents of the mechanical quantity Q. Once the dimensions of the mechanical quantity Q are known, the way the initial speed varies with the energy is known. Different choices are possible for the quantity Q, associated with different values of the exponent x, and so leading to different scaling exponents 1 over 2 minus x for the relationship between the speed c0 and the energy E. Depending on the context and the choice of Q, the initial speed may have different names, like the flame speed or the ablation speed. The case we'll consider today is when the speed is an ejection speed, which corresponds to the case x is equal to 0. That is when Q is simply a mass, for which we'll use the lowercase m as a symbol. This speed is also sometimes called the Gurney speed. Let's see where the mass m comes from. Let's start again with Trinity. If the first couple of data points are used to estimate the initial speed, we saw that this speed is around 100 km per second. Not bad. Can this speed be understood as a ratio of energy and mass? We'll be prudent and use an approximate equality, because as usual we're neglecting numerical factors. For instance, some may prefer to put a 2 over here. The reason being that the equation can then be rearranged to look as the definition of a kinetic energy. From this perspective, the entire energy of the explosion is initially expressed as the kinetic energy of something of mass m moving at speed c0. We won't get into the details here since we're most interested in rearranging the equation so as to obtain a mass from the speed and energy. For Trinity, we know the energy, and we've just estimated the initial speed by fitting the first couple of data points. So if the speed is to depend on the square root of the energy E and mass m, then this mass can be calculated and it must be around 9 tons. We're speaking here of a metric ton, that is 1000 kilogram. Where are these 9 tons coming from? Well, first and foremost, the bomb itself. This gadget, as it was called, weighed almost 5 tons. The plutonium core was just over 6 kg, but it was surrounded by almost 2 tons of conventional explosives used as detonator, plus a bunch of other stuff adding to the weight. The neutron initiator, the initiator cavity, the uranium reflector, etc. But where does the bomb stop and the rest of the world begins? To quote Julian Mack's 1946 report, the gadget cradle rested on a steel-supported wooden platform. The floor was 1.1 meters below the gadget center and extended symmetrically in a 4.65 meter square. The platform consisted of a steel frame of a mass of 1.48 tons and an oak wood floor of 1.17 tons. And above the platform there were 1.43 tons of steels, in addition to the metal house of 0.68 tons. So adding the mass of the gadget to the different parts of the bomb cab, we do find a mass around 9 tons. So overall, the 9 tons inferred from the initial speed seem to be almost exactly equal to the total mass of solid materials in the immediate vicinity of the explosion center. So we may start with the working assumption that the mass m in the mechanical expression of the speed is the ejected mass. We can test this hypothesis by considering a conventional explosion, where the ratio between the energy and the mass is much lower. The energy is usually lower and the mass greater. A few weeks before Trinity, a test was conducted with 100 actual tons of TNT, so the energy of the explosion was 100 tons of TNT, which is around 4 × 10⁻11 joules. And the mass is, well, around 100 tons, neglecting the wooden platform. We do not have blast radius data for this historical test, but a replica was done in the 1960s, and it is part of our little collection since episode 2. This dataset is not exactly sensational, but it will illustrate our point anyway. The prediction of Taylor's regime without any dimensionless prefactor would give this. As usual, we can plug in a reduced Taylor set of constant, delta, to improve the fit. Delta equals 1.3 would bring better agreement with the data. Still, the range abiding to Taylor's regime is quite small. As in the previous episode, we simply label this regime by the pair of symbols for energy and density. We know that it is enough to recover the 2/5 power law from dimensional analysis alone. Should we be surprised that the agreement with the energy density regime is so limited? What's going on with the last few data points? Turning upward. We've seen this in the previous episode. The leading edge of the explosion is here measured from the shock front, and we know that the shock detaches and slows down progressively to join the sound propagation regime, the regime associated with the duo of stress, sigma, and density, rho. So it's not surprising that the agreement with Taylor's regime is lost after some time. Now, the deviation from Taylor's regime at early times is actually due to the transition toward the initial regime at constant speed. The speed is here given by the ratio of energy and mass, assuming E to be 100 tons of TNT and M to be 100 tons. As in the case of Taylor's regime, better agreement is reached by introducing a dimensionless prefactor close to 1. We call it delta with energy and mass as subscripts, so as not to confuse it with the Taylor set of constant. Better agreement with the data is reached if this prefactor is set around 1.5. The initial regime, that is, the energy versus mass regime, correspond to an ejection speed around 3 km per second for this explosion. If we compare Trinity and the 100-ton TNT explosion, it is quite clear that the initial speed of Trinity, around 100 km per second, is much higher than the 3 km per second of the 100-ton test. Although we only have a few data points to illustrate this here, for both tests, the initial speed does seem to be close to the value predicted by the energy versus ejected mass regime. Can we use this simple formula for the initial speed on more examples of explosions? We've seen a lot of blast curves in the past episodes, and how much can the ejection speed be used to make sense of the very early dynamics? Of the datasets on this plot, only some cases have high enough time resolution to observe the initial regime, and a smaller subset also has reliable information about the ejected mass. This includes Trinity and the 100-ton test. For all these explosions, we can measure the initial speed and compare it to the square root of the ratio of energy and mass, as done on this plot. The measured initial speed is the y-axis, and the mechanical ratio is the x-axis. Both have the same units. Each point is an explosion. If the speed was always equal to the mechanical ratio, the data points should be on a line y equals x. The equality is only approximate. For each explosion we have a dimensionless prefactor delta, with values not too far from 1. 1.1 for Trinity. Delta is 3.2 for the teapot apple test. This is if we consider that the ejected mass m include everything in the vicinity of the bomb, as we did for Trinity. For teapot apple, O'Connell listed the mass of everything inside the bomb cap, which is the little shed around the bomb. The bomb itself was near 5 tons, and 12 tons of paraffin and 19.5 tons of magnetite were placed next to the bomb, over a 20-ton concrete floor. Considering all of this would lead to a dimensionless prefactor of 3.2. Only considering the bomb for the ejected mass would result in a prefactor of 1. This illustrates that determining the value of the ejected mass m can be a little bit tricky. The other data points are conventional explosions. The disks represent explosion in the atmosphere, and the diamonds underwater. They all have dimensionless prefactor close to 1, so the energy versus mass scaling of the initial speed seems pretty good for this set of explosions. Yet, much more data could be added to this plot, so if you know of any reference on this topic, let us know in the comments with the hashtag ejection speed. Trust in this energy versus ejected mass scaling can also be fostered by including the major league of the explosion domain, the supernovae. We're now talking of exploding stars. These explosions can be produced by a few different processes, including the so-called type 1a, like in this example. We won't get into the details here. The essential is that for this particular type of supernova, the energy and the ejected mass are known with some confidence. The energy of the explosion is around 2×10⁴ joules. Even expressed in megatons of TNT, this figure remains ridiculously big. Facing the energy is the ejected mass, around 1.4 times the mass of our Sun, so a mass around 3×10⁻30 kilograms. Now, in the early phase of a supernova explosion, the front does move at a constant speed, C note, around 10,000 kilometers per second. And we can compare this value to the speed predicted from the ratio of energy and mass. And the agreement is good, and the star symbol in the corner sits right on the line. So the energy versus mass scaling of the initial speed is useful from supernovae to nuclear explosions and conventional explosions, large and small. So for the nuclear and conventional explosions in our collection, the ratio of energy and mass seems a good predictor of the initial speed C note. But this set is only a fraction of the datasets where an initial speed can be measured. In some explosions, no ejected mass is available, in particular for laser-induced explosions. Consider the experiment from Grun and co-workers, published in 1991. What you see here is a picture of the blast 243 nanoseconds after the beginning of the explosion. In this context, the time t equals 0 does not correspond to the detonation of a bomb, but to the impact of a laser onto a polystyrene foil. In this case, the energy of the laser is 200 joules. The very fast laser pulse generates a small pocket of ablation plasma, the seed of the blast. What would be the mass m in this context, to be used to compute the initial speed? It is the mass of the ablation plasma, which we can estimate from the data. As in the case of larger explosions, the blast radius follows two consecutive power laws. One of the straight line is the energy density regime, that is Taylor's regime, that is the 2/5 scaling. At earlier times, the radius is proportional to time. The speed of the blast in this case is around 200 kilometers per second. As we've seen, this constant speed regime can be understood as an energy mass regime. So the ablation mass can be estimated from the energy input E and the initial speed, giving a mass around 5 micrograms. So, although a mass is not directly provided as an input, like the mass of a bomb, it can be inferred from the energy and the measurement of the initial speed. The early dynamics of laser-induced explosions are essentially similar to those observed in conventional and nuclear explosions. The same three mechanical quantities are at play: energy, mass, and density. When does the transition occurs between the initial regime and Taylor's regime? What is the associated size at this crossover? We're now going to see that this critical size L corresponds to the boundary beyond which the swept-up mass of surrounding medium becomes greater than the ejected mass. We've played this game before. In the previous episode, we've seen that the intersection between different regimes yields remarkable space-time points. We use the symbols L and tau for the coordinates of this new point. When we will need to differentiate it from other remarkable points, we'll use subscripts, recalling the mechanical quantities at play. Here, energy, mass, and density. First, let's talk about the length. This length does not actually depend on the energy of the explosion, just on the ejected mass m and the density ρ of the surrounding medium. We've done this kind of math in the previous episode, so let's go a little faster on this one. From the first regime, we can get an expression for the time tau of the intersection. The equality is approximate because we neglect dimensionless constants, the deltas, for now. And from Taylor's regime, we know another relationship between L and tau. Using the expression for tau, the only thing left is to simplify the energy disappears, and we finally get a length depending solely on the ratio of ejected mass and ambient density. How nice to go through this messy algebra to get a simple answer in the end. What is this formula? Rearranging, this is stating that when the radius d reaches the value L, the swept up mass is equal to the ejected mass m. We know the ejected mass m. What is this swept up mass? We know that the left-hand side is a mass because the density rho is a mass per unit volume, so the dimensions of its product with L cubed is a mass. The swept up mass can be defined for any explosion size d, and so it is a variable, implicitly depending on time, since the size d is a function of time. As the volume of the explosion grows, it is replacing a volume of ambient medium of density rho. It is sweeping up the ambient medium. In the initial regime, the swept up mass is smaller than the ejected mass, and so it is the ejected mass itself that is the resisting factor facing energy. For Taylor's regime, the swept up mass is larger than the ejected mass, and the density of the ambient medium becomes the resisting factor facing energy. The crossover size comes from the ratio of mass and density. We've seen this in the last episode. By considering the intersection between two regimes, we get a third regime for free. Here, it is the mass density regime. For this laser-induced explosion, the threshold length between the initial regime and Taylor's regime is just a few millimeters. But the same physics are at play for much larger explosions, like Trinity, while the transition between the two consecutive regimes occurs when the radius of the blast is around 20 meters. This is how much swept up air is needed to make up for the 9 tons of the ejected mass. This understanding of the transition between the initial regime at constant speed and Taylor's regime was very much present in the minds of the physicists working on the Manhattan Project. The crossover length as a ratio of ejected mass and ambient density was for instance mentioned in the 1947 Los Alamos report led by Hans Bethe, might even have originated there. The principle is simple. The greater the mass, the bigger the crossover length. And the smaller the density, the bigger the length. And at this game, the champions are supernovae. This is Tycho's supernova, an astronomical explosion that has been going on since 1572. The picture here was taken in 2003, so 431 years since detonation, if we may say. And it is just getting started. The size of these things is so large that meters are flagrantly irrelevant units. The small scale bar that you see in the corner is 1 parsec, which is equal to about 3×10⁻16 meters. But the unit of length that we should really compare this supernova to is the one coming from the ratio of mass and density. Here, the ejected mass is around the mass of the Sun, 2×10⁻30 kilograms. What about the density? Isn't space empty? Well, not quite. The density of interstellar space can vary a bit, but a good order of magnitude is 1 atom per cubic centimeter. And these atoms are mostly hydrogen, so the density turns out to be on the order of 10⁻21 kilograms per meter cube. Pretty empty in comparison to what we're used to, and yet, little by little, the swept up mass of this near vacuum builds up, such that when the radius of the supernova remnant reaches around 10⁻17 meters, the density actually starts to be the dominant factor resisting the energy of the explosion. This crossover length is equal to 4 parsecs, and Tycho's nova is right there. It has finished its 4.5 century long first phase of expansion at a constant speed, and it is entering Taylor's regime. Not only does the mechanics of the situation produce a characteristic length, but as in the last episode, they provide a full system of objective units that simplify the description of the consecutive regimes of the explosion. The interplay of energy, mass, and density provides units for space and time, just like energy, density, and stress produce the Hopkinson-Kranz units in the previous episode, best suited to describe the late dynamics of explosion. No particular names seem to stand out for the early units, so we just refer to them by the trio of mechanical quantities that they are based on. We're going to see so many of these systems of units on this channel that this notation will be more practical anyway. Let us know in the comments if you think that these units deserve to be named after someone. Please use the hashtag nameunits. Returning to Trinity, we know that the system of units best suited for the early dynamics of explosion must be centered at the junction between the three regimes built from energy, mass, and density. We know the formula for the space coordinate of this point, and we know that the time and space coordinates are connected by the initial speed c0, coming from the interplay of mass and energy. So plugging in the expression for the size, we get a formula for the time. We're getting used to this. Last episode with the Hopkinson-Kranz units, that is delay units, we had seen the only length and time built solely from energy, density, and stress. Now, with the early units, we're seeing the only length and time built solely from energy, density, and not stress, but mass. In studies on explosions, these units have been around at least since the Manhattan Project, and they are usually presented quite clearly in studies on supernova remnants. We know what to do with these units. We can look back on our collection of explosions with fresh eyes. We know meters and seconds are inadequate units. Instead, for each explosion, we can compute the value of the early length and timescales, and replot everything in these more objective units. The time and space coordinates are now dimensionless. The logarithmic origin of this plot corresponds to a size equal to the characteristic length, and a time equals to the characteristic time. You may have noticed that, as in the previous episode, the units of length and time have little asterisks. This is to recall that they include the dimensionless constants close to 1, like the Taylor set of constants, the deltas of the different regimes. So the units of time and space are approximately equal to the units built solely on energy, mass, and density. We discussed how to get the dimensionless prefactors right in another video. Basically, the prefactors must be included in the units in such a way that the origin of the plot is exactly at the crossover between the initial regime and Taylor's regime. And we know that the crossover size is a regime in its own right, the mass density regime. The origin is the point of intersection of these three regimes. In this system of units, the equation of the initial regime is just dimensionless length equals dimensionless time. Taylor's regime is just size equals time to the power 2 over 5. And of course, the mass density regime is just dimensionless size is equal to 1. These three curves are master curves. For each explosion, if time and space are measured with this system of units, the evolution of the radius should fall on the master curves. We saw the same thing happen for the late dynamics in the last episode, so we won't give all the details here and just watch the pieces fall into place. Trinity is right here, and so are the other nuclear tests. The first two regimes of conventional explosions also follow the master curve. This one is the explosion of 100 tons of TNT we discussed earlier. Underwater explosions similarly collapse on the master curve if properly scaled, and laser-induced explosions are no exception. By getting rid of the arbitrary subjective units of length and time, the meter and the second, the similarity in the dynamics of these many explosions is revealed quite strikingly. A plot in standard units puts the emphasis on how big or small things are in comparison to us humans, for whom the meter and second make sense. A plot with objective units, like the initial units here, removes us from the picture, and the dynamics are measured with respect to their own remarkable turning points. These turning points only depend on the mechanical properties of the explosion, not on our standards. If instances of different explosions have the same coordinates in objective units, they are expected to behave similarly. And by the way, on a plot like this, we can even add Tycho supernova, which we know to be near the origin, that is, finishing the initial regime at constant speed and starting Taylor's regime. In subjective units, adding Tycho would compress all of the other datasets, making it really hard to imagine that the physics of these explosions is essentially similar. In objective units, if we highlight the data from Trinity, we see that Tycho's novas these days, that is 4.5 centuries since the progenitor star went supernova, is at a stage of its life comparable to Trinity around a quarter of a millisecond after detonation. The conventional dimensions are usually different, but both explosions are at a similar turning point in their evolution. At this juncture, the front of the explosion starts to slow down as the surrounding density ρ becomes predominant over the ejected mass m. However, we've seen in the last episode that at the intersection between the three late regimes, the front of the explosion can separate into multiple components moving at different rates. Can it also be the case here? Can part of the explosion carry on at constant speed? Yes, although the main front, the shock, slows down, some flying debris can carry on at the ejection speed. The existence of two different fronts is quite clear for Tycho. In a few places, the shock front in purple is pierced by ejected mass in yellow and red, which are still moving near ejection speed. For Trinity, the same thing was at play, with spikes and blisters emerging at the transition, although the pictures are less impressive. This is another test, Red Wing Mohawk, a moment after the transition between the initial regime and Taylor's regime. Bulging toward the right side of the screen is a jet of ejected mass, which was engineered by a purposely asymmetric bomb. More common even for symmetric bombs are the many dark spots on the comparatively brighter shock front. We only point to some of them. These spots are due to small debris that have flown through the shock front, moving faster than it. So on this plot, the explosion front only seems to go from the initial regime to Taylor's regime, but it is only because we are not tracking the trajectories of the flying debris, which can be as fast as the initial speed. How much of these debris fly off depends on differences in the initial distribution of mass m. For instance, these two pictures from a 2006 study by Gary Settles show two different explosions captured at the same time. Both show a shock front around 1 meter in diameter. Both explosions are produced by 1 gram of TATP, which correspond to around 3000 joules. Both explosions are in the air, so with the same ambient density and pressure. The mechanical quantities are identical. Yet, the only difference is that the container of the explosive on the right fragments in small pieces, which fly off ahead of the shock. So even if we have not paid much attention to these debris so far, they are there and they can be deadly. So just like in the previous episode, the intersection between the three early regimes also allows for multiple paths to be taken and multiple definitions for what we call the front of the explosion. Now, these early units are very nice to describe what is going on, well, in the early dynamics of the explosions. But of course now, the late dynamics do not overlap anymore. It is like having a short blanket on a cold night. Pull it over your neck and your feet get cold, cover your feet and your neck gets cold. In the next episodes, we will see how to knit a blanket with the right size.